Right, now let's get on to hydrogen. A few notes first. This is more about of a historical context. The pattern of spectral lines in hydrogen was analysed by Balmer in 1885, who found that the wavelength of the lines are given by here. Lambda equals n squared over n squared minus 4 multiplied by 365 nanometers, I think that's pronounced, with the values 3, 4, 5 and 6, the n values. The 4 lines in the Balmer also suggested n might take higher values corresponding to ultraviolet region of the spectrum. This was before quantum mechanics really was taken off, I believe. But anyway, let's not go off on a tangent. Now the reduced mass of hydrogen is here given by mu, where me equals the mass of the electron, mp equals the mass of the proton, which is just a product and divided by the sum of them, and the mass of the proton is 1,840 times the mass of the electron. So the reduced mass is only slightly less than the mass of the electron. So combining various constants, including h bar, we can define a quantity with dimensions of length given here, a0, and a quantity with dimensions of energy here, er. Now a of 0 we've come across before. It's the Bohr radius, and is the Rydberg energy. Now the time-independent Schrödinger equation, viewed from the center of mass, the energy of the two-particle system can be written here, where the first term is the kinetic energy of the particle and with the reduced mass mu, and the second term is the electrostatic potential energy of the electron and proton, with the energy 0 being at infinity, and the corresponding Hamiltonian is given here. We can now build the Schrödinger equation here and find its stationary state solutions, where a psi of r satisfies the time-independent Schrödinger equation, and it is an eigenfunction that satisfies the eigenvalue equation. Now the potential energy function, the V of r equals minus e squared over 4 pi epsilon naught r, which you'll recognize from classical electromagnetism. This is what's it called now? The Coulomb potential is spherically symmetric, which is in essence Coulomb's law. In spherical coordinates, it depends on the radial coordinate r, but not on theta and phi. Now the from del squared we obtain this, which we wrote out I think a couple of times now. Now the term L squared depends on theta and phi, so we separate R of our ear, which is our radial, and then our spherical harmonics. The separated equations are given here, here and here. We've been through this a few times now. Now we already know the eigenvalues of L squared are L plus 1 h bar, so the angular momentum quantum number is K here, L plus 1 h bar squared, and the radial equation becomes this. We can now use an identity here to rewrite this equation, and we're letting u of r equals r, uppercase r here, and we will get this here, and this is the reduced radial equation, and u of r is the reduced radial function. We are only interested in r greater or equal to 0, because obviously the radius has to be greater than the center of the nucleus of the atom. Otherwise it's a singularity. It's infinitesimal. It doesn't make any sense. But R sub R doesn't diverge as R goes to 0. We can set U of O equals 0. We assume U of R does not diverge as R goes to infinity. Otherwise, we should not be able to normalize our radial solution. And here's a few solutions of the radial equation. Should I say, we'll go on the solution of the radial equation. First, we consider the expected limiting behavior of small and large r. Simplify, define two simultaneous variables. Rho is r over a, which this you probably recognize if you've taken quantum mechanics before anyway. This it comes up within polynomial solutions, polynomial multiplied by this. What are these polynomials now? I think they're Laguerre polynomials. But anyway, now we note that here d squared over dr equals 1 over the Bohr radius squared, d squared over d rho squared, and h bar squared multiplied by 2 mu equals the Bohr radius multiplied by the Rydberg energy. And here is our Coulomb potential without the r term, and so we obtain this equation here. Now we are looking for bound energy states because energy 0 is at infinity. Any bound state we will have for any bound state we'll have a negative energy. So epsilon is negative. We write epsilon equals minus rho squared, minus beta squared. Sorry, where beta is the real and positive. So we will get this equation here. Now as r goes to infinity, therefore rho goes to infinity, the potential energy term becomes this here. And this you should recognize as a standard differential equation, so it's very straightforward solutions. I'll go through a whole lecture series properly on differential equations because I think that's probably the most important thing that underpins all of this, and I'll put a lot more time into that. And I'll walk through it step by step, unlike these that are written down in advance. But anyway, the general solution here is given here, where C and D as always are constants. Now showing this is a solution. Now substitute UP equals C e to the minus beta rho plus D e to the beta rho. Gives this after we're substituting into the differential equation. And for U of P here, so the solutions, so this satisfies the equation in any bound state. We expect the probability of finding the electron and proton to be very far apart to be very small, which obviously makes sense because if they're very far apart, it wouldn't be an atom, it would just be free particles moving around in space. So it's obviously a reasonable assumption. We don't have hydrogen atoms that are 1 meter big or anything, but yeah. So this means we can discard the D e to the beta over rho, which will just continue to grow without end, which diverges. So we set D equals 0. As rho tends to infinity, U of rho behaves like C to the E minus beta rho. Limiting behavior for this is limiting. Now we go on to limiting behavior for small r. Suppose L does not equal 0 in this case. The centrifugal barrier dominates at low rho, and we get this. We take a trial solution. We're going to see where the flawed logic go. We come across some flawed logic going through these calculations. I'll point it out in a bit. But U of rho equals rho of K. Now we substitute these into the above equation, we get this. K minus 1 equals L plus 1. And our solutions, obviously K equals minus L, and K L plus 1. So the general solution for small rho would be this here. But now now as rho goes to 0, U of rho behaves like here, B rho to the L plus 1. So a nodeless solution where we're given U of rho behaves like E to the minus beta rho at large rho and rho L plus 1 at small rho. So we try a solution of this form here as our trial solution, which is a candidate for the lowest energy reduced radial eigenfunction. What values L and epsilon take? We know L equals 0, 1, 2, 3, thus epsilon equals minus 1 over L plus 1 squared. Then we can take minus 1, minus 1 quarter, minus 1 ninth, minus 1 16th, and so on. So E equals 1 over n squared, where n equals 1, 2, 3, so on. So each value of L equals 0, 1, 2. We found solutions of U of rho, C, L plus 1, E to the minus rho over n, where n equals L plus 1. Now we recall that rho equals R over A0, the Bohr radius, and our function of R, U of R, is U of R over R. We get this, which may look familiar if you've come across radial solutions of the Schrödinger equation before. But since L equals n minus 1, there is one solution for each positive integer n. The corresponding energy eigenvalues are E n epsilon E sub r, the Rydberg energy, which is here because minus the Rydberg energy over n squared. So n equals 1, 2, 3, and so on. This is a special case for a nodeless solution. Oh, and that's it for this one.